Today we're going to start chapter 4 in statics, and the title of chapter 4 is Equilibrium of Rigid Bodies. So today we're going to cover section 4.1, and I'm going to work problems for as long as I have, which is close to an hour. So I have 3 problems that I would like to work, and I'm going to start in on them. But chapter 4 is sort of the culmination of everything that we've talked to up to this point. And basically we've talked about forces and summation of forces, and we've also talked about moments and summation of moments. So for a particle to be static, in other words, to not be moving, the summation of forces in all vector directions has to equal 0. For a rigid body that has shape and size, also the summation of moments have to be equal to 0. So that's what we're going to be doing today, is working with those 2 principles, as well as considering the reactions that come from supports. So when we look at, these are the 3 problems that I'm going to work, but in your textbook on page 173, you'll see the types of forces that are associated with some different types of support. And they all sort of make sense. For example, if you have a roller on a flat surface, any force that's applied in the x direction is going to cause movement. So in other words, a roller is not designed to bear a horizontal force in this configuration. It only bears a vertical force. So other forces are shown here so that you can refer back to this when you're doing free body diagrams and do not know what the reactive forces might look like. But having said that, the basic idea that we're going to talk about today is for equilibrium to occur, we need all of these conditions met. The summation of forces in the x direction, the y direction, and the z direction all have to equal 0. And similarly, the moments in the x direction, the y direction, and the z direction about any given point have to be equal to 0. So in 3 dimensions, we have 6 equations of equilibrium that must be satisfied. Section 4.1 talks about equilibrium in 2 dimensions, and that's our topic for today. So if the 2-dimensional forces are in the x and y direction, we can say that the summation of forces x and summation forces y have to equal 0. And then in terms of moments, if all of our forces and all of our moment arms are in the x and y plane, the moments are all going to be in the z direction coming out of the page or into the page, and that they will also have to be equal to 0. So what we're going to do when we look at these 3 problems, 4.1, 4.7, and 4.40, is to set up a good free body diagram, determine what the forces are acting on that body, and then set up these 3 equations required for equilibrium and use them to solve for our unknowns. So the first thing I will do is get the problems from our textbook, and we'll take a look at them. Problem 4.1 talks about a gardener who has a 60 Newton wheelbarrow, so that's the weight of the wheelbarrow. She's using it to transport a 250 Newton bag of fertilizer. What force must she exert on each handle? So even though this is shown, you just see one of her hands, her other hand is back into the page, one assumes that she will have equal force on each handle. So we can just say that this is 2 times that force, and there's a reactive force of the wheel. Now, just like in the support section that we just saw, the force on that wheel is only going to be vertical. And so using that information, we can determine what all of the unknowns are here. Okay? So for 4.1, if we draw a picture, we have a wheel, and if the wheel, let's do it, and then we have the 60 Newton, excuse me, weight of the wheelbarrow pushing down. We have the 250 Newton weight of the fertilizer pushing down, and then one would assume that the gardener is pushing up. So I'll call that 2 times the force of the gardener. All right, what's going on with the wheel? If these are pushing down, there's also a vertical force at the wheel pushing up. And we know it's vertical because as a wheel, it's not going to bear anything in the horizontal direction. All right, now we are told some dimensions. We're told that we have 0.15 meters between the point where the wheel is in contact with the ground and the acting mass center or weight center of the wheelbarrow. And then we have another 0.15 meters between the mass center of the wheelbarrow and the weight center of the fertilizer, the weight center of the wheelbarrow and the weight center of the fertilizer. And then we have 0.7 meters between the point where the gardener is pushing up and the weight of the fertilizer is pushing down. Okay, what we're looking for in this problem is f sub g. All right, so the first thing we do is set up our equations. We know the summation of forces x have to equal 0, which is, it's a trivial equation. There's nothing going on in the x direction. So we also know the summation of forces y equals 0. So going up, we have the force of the wheel and 2 times the force of the gardener. Going down, we have 60 newtons and 250 newtons. And we know that in order for this to be an equilibrium, those have to sum up to 0. But what we get here is that we have one equation. These added together would be 310, and they become positive on the other side of the equation. So we have 2 unknowns, but only one equation, which means algebraically that we need a second equation, and that equation is going to be our moments. All right, so we have the moments in the z direction about any point is equal to 0. If I look at this free body diagram, if I take the moments about the wheel, that means that the force of the wheel will not enter into the equation, and I can solve directly for the force that the gardener is exerting on the handle. I could take it, it would be equally true about any point, but if I took it somewhere else, I would end up still with 2 equations and 2 unknowns, and I have to solve them simultaneously. So if I just go straight to the wheel, eliminate that force because it eliminate that moment because the moment arm is equal to 0, then it will be easier to solve. The other thing is that each of these forces is vertical, so I'm concerned with the horizontal distance, and I'm concerned with the direction of spin. The 60 Newton, if I put a pin here in the wheel, would tend to spin clockwise. This would tend to spin clockwise. This would spin counterclockwise. So I know clockwise is negative. Clockwise is negative. Now here we're taking the moments about the wheels, so this is 0.15 to here and another 0.15 to here. So that's 0.30 meters to there. And then we have 2 times the force of the gardener, which is positive because it's counterclockwise, times the sum, 0.3 times plus 0.7, which is 1 meter. And those things all added together have to be equal to 0 in order for equilibrium to be satisfied. So I can just solve for 2 times the force of the gardener. When this comes over, it's positive. So if I take 60 times 0.15, that value is 9 Newton meters. 250 times 0.3, that value is 75. Once again, I'm leaving the f sub g on the left-hand side of the equation, bringing the other 2 to the right-hand side where they both become positive. So then f sub g is going to equal 9 plus 75 divided by 2, just doing a little bit of arithmetic there, and I get 42 newtons. So that means, therefore, the gardener pushes up with a force of 42 newtons on each handle. It means she's pushing up with a total of 84 newtons, but it's evenly divided, we're assuming, on two different handles, so 42 on each. All right. The next problem I wanted to work is 4.7. And I have taken it out of my book and put it somewhere. Here it is. All right, 4.7, right here. We have a T-shaped bracket supported by that supports 4 loads. Determine the reactions at A and B if A is 10 inch or if A is 7 inches. All right, I'm just going to do one of these. I'll choose 7 arbitrarily. The one, if it's 10 inches, I'll choose this. 10 would work exactly the same way. Now, here's the deal. We have these 4 pulling down. That means B is going to be pulling up. And if you look at these weights, though, A is not capable of pulling up. It's going to be pushing down, right? And if you think about this, as these loads are larger, or have a larger moment, I should say, that A is going to be pushing down on the bar. So, basically, my free body diagram is going to look like this. We have the reaction at A pushing down on the bar. We have a 40-pound load down here. We have a 50-pound load down here. We have an opposing reaction at B pulling up here. Then we have a 30-pound load and a 10-pound load. Okay, we're also told that this distance is 6 inches. This distance is also 6 inches. I'm using the 7-inch distance here, and this distance is 8 inches. All right, same thing. We have 2 dimensions. We have equilibrium. We need to solve for A and B, the reaction at A and the reaction at B. So that means we have to have 2 equations in order to solve for 2 unknowns. So the first is going to be the summation forces in the y direction, which have to equal 0 in order for equilibrium to be met. We have, if we call this up being positive, we have R sub B minus R sub A minus 40 minus 50 minus 30 minus 10, all in pounds, equals 0. So I get RB minus RA is equal to, these all come over as positive to the right-hand side of the equation. So these 2 are 50, that's 130 pounds. So we know that R sub B minus R sub A has a value of 130 pounds, but we don't know what either of these are. So then we need to take the summation of moments about some point and set that equal to 0 as well. Okay, we could take moments about A, and we would eliminate the reaction at A. But if we take the moments about B, we'll eliminate this and this, because neither one of them has a moment, because there's no moment arm. So I'm going to take the moments about point B. Then I just have to be concerned with my direction of rotation. R sub A, if I put a pin here at B, is going to rotate this in a counterclockwise manner. So it's a positive R sub A, whatever that is, times 12 inches, because that's the distance from here to here. Then I also have this positive 40 pounds, which is operating 6 inches from B. Then neither of these, R sub B or the 50, produces a moment. So I come over here, and that's going to be a clockwise moment, 30 pounds times this distance, 7 inches. And last but not least, a negative 10 pounds times this distance of 15 inches. And all of those things together have to sum up to be 0. All right, well, that means I can solve directly for R sub A here. And I can say, if I'm going to take my 2 negative terms, 30 times 7 is 210. And when it goes from left-hand side to right-hand side, it becomes positive. 10 times 15 is 150. And again, it becomes positive over there. But 6 times 4, this is 240. It's positive on the left, so it becomes negative on the right. And that's r sub a times 12, so I can divide that entire thing by 12 inches. And this would be pound inches. So inches cancel out, and I'm left with pounds. So r sub a has a value of 210 plus 150 minus 240, or a value of 120 divided by 12, which is 10 pounds. So that means r sub a pushes down with a force of 10 pounds, which is negative. So I have r sub b minus 10 is equal to 130. R sub b, oh, that's just minus. I'm trying to think about this for a second. The harder that pushes down, the bigger r sub b has to be. So this is just a single minus. Sorry about that. So that means it's 130 plus 10, and that r sub b is 140 pounds. Now we can go back and check that, and we can see if we have 10, just by forces, 10 going down plus 40 going down is 50, plus 50 more going down is 100, plus 30 is 130, plus 110. That means that r sub b has to pull up with a force of 140 pounds. So the answer to this problem for a distance of 7 inches here is r sub a is 10 pounds pushing down. R sub b is 140 pounds pulling up. All right, and the last problem I would like to do today is 4.40. Okay, we're going to use the same principle, two-dimensional equilibrium, how everything gets solved. So, 440, the problem shows that we have this light bar from A to B, and it supports a 15 kilogram block right in the middle. There are rollers at A and B, so we have to think about what direction those rollers will support. They're going to be perpendicular, so A is just going to be able to support a horizontal force, or excuse me, a vertical force, and B is just going to be able to support a horizontal force. In other words, it has to be perpendicular to the surface of contact. Rollers at A and B rest against frictionless surfaces. Horizontal cable AD is attached. Determine the tension in AD and the reactions at A and B. All right, so here's what we have. We have this bar being acted on by these forces. This is the reaction at B. This is the reaction at A. This is the tension in AD. And this is the weight, which is mass times gravity. Those are the forces that are acting on this bar. We're told that the mass is 15 kilograms. So if we take 15 kilograms and multiply that by g, which is 9.81 meters per second squared, we take 15 multiplied by 9.81, and that value is 147.15 newtons. Now that's way too many significant figures. It should just be 147, but until I get to my final answer, I'll leave it that way. All right, this problem we have both horizontal and vertical forces, don't we? So in the horizontal direction, summation forces X equals 0. We have that TAD, which is positive, minus RB is equal to 0. So we know that the magnitude of the tension and the magnitude of RB are going to be the same. They're just opposite in sense. In the Y direction, we know that R sub A, which is positive, minus the 147.15 newtons has to be equal to 0. So we can solve instantly for the value of R sub A. And I'd say in the final analysis, 147, even 150 is better in terms of significant figures. But I'll just leave it at 147. It's a little bit over specified, but that's okay. All right, in the x direction, we don't know anything yet, do we? We still have two unknowns. So that means we need a third equation. The summation of moments about any point on this bar have to be equal to 0. I need to know R sub B. And I also need to know TAD. My feeling is if I take the moments about A, I'm going to be able to get R sub B right away because I have the weight and it's a vertical force. So I need that horizontal distance and I need this vertical distance, and I should immediately pop out R sub B. So I'm going to take the moments about A to get rid of this force and get rid of the tension in terms of the moments. All right, so if I put a pin here, the weight is going to spin this clockwise or negative. So that's 147.15. Since that's a vertical force, I need the horizontal distance, which is 250 millimeters from the problem statement. Then R sub B is going to spin it counterclockwise, and the vertical distance from point A to B is 350 millimeters. And those two things sum together equal 0. That means R sub B, if I bring this over to the other side, we have 147.15 times 250. That would be R sub B times 350 on the left. So I divide by 350, and I get my value of R sub B, and it will be in newtons because these are both in millimeters, so they cancel out. So 147.15 times 250 divided by 350, and I get a value of R sub B of 105 newtons. All right, well, if I go up to this equation, I can then say TAD is equal to R sub B, which I just found to be 105 newtons. And I've now found all of the answers that I need for this problem. All right, everybody, so that should get you going on the homework problems. All of the technique that we have used to this point in terms of finding forces and moments and resultants will all come into play in Chapter 4. The only piece of information we need to add is the idea of equilibrium of moments. Moments have to equal 0 on that rigid body. So in 2 dimensions, we only have one moment equation, which is perpendicular to the plane that we're working in. So if you think about the board or the piece of paper as being the XY plane, we only have the moments in the Z direction summed to 0. Then we have forces in the X and forces of the Y summed to 0. So we have 3 equations in order to solve. But the method for doing this starts with a good free body diagram. And the other new piece of information may be how the reactions, or how the fasteners, or how the points of contact, what kind of reactions will be in each of those. And there's a little table in your book, and if you need more help, please let me know. Have a great day.